Okay, so hi everyone. I'm Tony, and I and Rebecca, I'm going to do a quick switch over at some point. We're going to talk about Rust and OpenSHMEM. So I'm going to talk about what OpenSHMEM is for the one or two of you who have never heard of it before, and what this project's about. And then Rebecca will get into the weeds of a quick overview of the Rust language, and then all of the hard work for Rust interacting with OpenSHMEM. So she did all the hard work, so it's only fair that she gets to showcase. So OpenSHMEM, as you probably all know, is a partition global address-based library, sits on clusters, works over interconnects like InfiniBand. It can use various shared memory transports when they're supported. So UCX, for example, can handle KNEM and XPMEM. It's a library with point-to-point RMA, context for partitioning communication, has collectives over teams or groups of nodes or processes, has atomic operations, distributed locking mechanisms, and dynamic memory management. Open specification, community-driven. So go to the website and everything's free and open, and jump onto GitHub and everything's accessible to you. There's various implementations, some open source ones, and there are various various vendor implementations such as HP, Cray, IBM, and so on. The project funding for OpenSHMEM that we work on comes ultimately through LANL, Los Alamos. And we were asked to look at interfacing OpenSHMEM with newer languages like Rust and Go. So I've been doing some stuff with Go, and I started the Rust thing, and then we thought it'd be a great idea to find a good student to work on it, and we luckily got hold of Rebecca. So the various goals within this project is the safety aspects, the security of it, speed and usability to the end user, the programmer who wants to use Rust in a paradigmatic way. So we work on the reference implementation of OpenSHMEM. So it's based on top of UCX for communications, which is sort of why we're claiming this is relevant through transitivity. We use PMIX for wire up. We have a collective library that we developed along with collaborators in this project, although I think we probably should move to UCC or similar at some point. There's the UCX diagram. So we sit on the second box from the left at the top, and we talk to all of the UCP layer, which allows us to target atomics and RDMA and barriers and fences and all those great things. And we don't touch UCT, we just work at UCP. So that means we can run anywhere that UCX can. Here's the architecture of our implementation. We run through, say, a job schedule like Slurm or similar, or you can run it bare on a command line. So we have PMIX server, such as that in MPI run or the PERT environment. Each rank or PE of the program is a PMIX client, and it provides the OpenSHMEM layers on top of UCP, which then obviously goes down and then starts talking to the hardware. Okay, so that's just setting up what an implementation of OpenSHMEM tends to look like. So what I asked Rebecca to do was to look at extending a bare bones Rust interface to OpenSHMEM. So it's automatically generated, which you'll describe. And what we decided to do was a proof of concept interface in a special student project using OpenMPI's OSHMEM as being like the most likely OpenSHMEM that anybody else would ever see in public. So this is my handover point. So Rust is a newish language, and it sort of sits where C and C++ have been used to being in charge. So it looks a bit like C, C++, Java, C-like syntax with braces and the same sort of minimal keywords. There's been efforts recently to put it into the Linux kernel and also in userland tools. So like the core utils, bin utils, that kind of thing, rewrite them in a safer language than C. There's the documentation of Lang, if you want to go and look. You haven't looked at it yet. And Rust has useful safety guarantees, which is the motivation. So we were tasked with looking at, so how do we get Rust talking to, or looking like it can talk to legacy style application layouts, say for national labs and similar people. So this is my handoff point to Rebecca. So I'm going to quickly stop sharing, and then she can jump in and start from slide 9.
Mm-hmm. Yep, I'll share my screen right now. Does everyone see my screen?
Yeah.
Okay, perfect. Yeah, so my name's Rebecca Hassett. I'm a master's computer science student at Stony Brook University, and I'll be talking about the Rust OpenSHMEM interface. So as Tony said, Rust is a new systems programming language. It's designed for performance, ease of use, memory safety, and it has much better performance than languages such as Java, because instead of using garbage collection, it uses a more lightweight process known as the borrow checker, which we'll discuss later. And also an interesting point is that Rust is considered to be an ahead of time compiled language, which means you can compile a Rust program and its executable can be run on any other machine, even if it doesn't have Rust installed. Whereas a language like Python or JavaScript, you would need those languages to be installed to run it. So first, I'm going to be talking about how Rust prioritizes safety. So in C, even the most experienced programmers can make mistakes such as dereferencing null pointers or data races, and Rust prevents these errors at compile time with strict ownership rules and the borrow checker. So it prevents these issues here. It's also important to note that Rust limits but cannot entirely prevent deadlocks and memory leaks, which are not considered to be memory safety issues. So here's an example of an OpenSHMEM program that we later converted into with Rust. Right here, it's in C. So here you can see the counter variable, that's a raw pointer, and it's really up to the C pointer to guarantee that pointer, that it's valid, and also that we're not freeing it before it's being used. So then here in Rust, I'm going to talk about the borrow checker that's used. So in Rust, every time a variable goes out of scope, so these curly braces here, every time it's initialized and it goes out of scope, it's automatically dropped. Also, when a variable is moved into another function, its ownership is moved into that function and it can't be used after that. So here, this variable x, its ownership is moved into the drop function and it cannot be used in this print line function. So we get an error here. So that's good because it prevented it from being used after it was dropped here. So for safe Rust, the compiler guarantees that it will catch all of these unsafe memory errors, taking a great burden off the programmer's shoulder. But unsafe Rust places some of that responsibility back onto the programmer so that they can have extra capabilities when working with memory, such as dereferencing raw pointers, calling legacy code in C, accessing mutable static variables. So like if you call a C function, Rust can't guarantee that everything happening in these C functions is safe if you could be freeing the variable or something. And it's really up to the programmer in Rust to be a detective and guarantee that we're always preventing and abstracting away this unsafe code. You may wonder, well, why do I even want to use unsafe Rust? I would love to just let the compiler do all the work for me, but you really can't prevent yourself from using it because there's so much legacy code that we need to call in other languages. And even in Rust, you can implement low-level systems such as operating systems where we're accessing the memory directly. And even if you do use safe Rust, if you look under the hood, you'll realize that Rust is unsafe just like any other language. So here is a snippet from the Rust standard library, very common data structure that's used, this vec data structure, and it's the push function. So there's an unsafe block inside of there because we're writing to a pointer. And if you were to use grep and look through the entire standard library, you'd see hundreds of hits that there's unsafe code everywhere in the standard library. So this is an example of using unsafe code in Rust. This is dereferencing raw pointers. So on the left, this is a valid example of using raw pointers. We're casting references to raw pointers and dereferencing them. You might wonder, well, what's the difference between a reference and a raw pointer? Well, references follow borrow checking rules and the ownership rules, but raw pointers don't. So references, you can have as many immutable references as you want. You can have as many reads as you want, but you can't have a mutable reference and another reference at the same time. Then you could have data races. But here in this example, it's valid because our write happens after our read operation. On the right, it's an invalid use case of raw pointers. We're creating a raw pointer to an arbitrary memory location. So that could be null, the data might not be aligned. So if a user were to wrap this in unsafe code and dereference it, there'd be undefined behavior. And it's really the programmer's fault for introducing unsafe code inside that unsafe block. Here's another example of unsafe code in Rust. In other languages, you've probably seen where arrays being initialized element by element, but Rust doesn't allow partial initialization of arrays because you could end up accessing an uninitialized part of the array. So Rust has unsafe workarounds for that. So here we're initializing element by element with this maybe uninit struct. And then in the unsafe code, we're calling this very unsafe function called transmute, which converts the maybe uninit type to the expected type, which is a box U32. And the transmute function is very unsafe because you can take some bytes and it forces it to be interpreted any way that you ask it to. So let's say in memory, you have the number 3. If you ask it to be interpreted as a bool, of course, that's going to lead to strange behaviors. In Rust, the unsafe keyword has 2 use cases. It can either be used here as a unsafe function. So it's really up to the person calling this function here to guarantee that they're maintaining memory safety. They have to look in the Rust documentation for the unsafe code and check that they're passing in the right parameters. They also, when you're calling an unsafe function, you have to wrap it in an unsafe block. On the right side, this is considered to be an unsafe block. So we're kind of creating like a safe API function around the unsafe code. And it's really up to the programmer implementing this function to make sure that they're handling everything safely. So the person calling it doesn't have to worry about the safety guarantees at all. And this is really the crux of Rust, is that Rust is essentially a toolkit that turns dangerous code into safer code for all of us to use so that we don't have to worry about all of these tedious memory safety issues. So here's like an example where you would look at the function documentation and you'd see an unsafe function, and there'd be many like safety requirements that you have to follow here, such as having a valid pointer and that it's aligned properly. And then here's an example of documentation for a safe function, and you don't have to worry about anything. The person who implemented this function guarantees safety, and you can pass whatever values you want, and it should always happen in a defined way. So now, how do we create these FFI functions? We can use this Rust bind gen program to generate the interface. You pass in the C header files, and libclang parses these files and type checks these files, and then here is the generated output. And all of these FFI functions are unsafe, so we have to wrap it around unsafe code, and this is where our safe API interface comes in. So here's some example of, so before I showed you that OpenSHMEM program in C, so this is how it's implemented in Rust. It's basically just summing from 1 to n the number of processes. So on the left, this is before I implemented the API. So you have to put the dereferencing of the raw pointer in an unsafe block. And on the right, this is the safe structure that wraps around the raw pointer. It safely handles all dereferencing and dropping of this pointer, so you don't have to worry about the unsafe code. So this is an example of our safe API. This is that SHMEM object, which wraps around the raw pointer. It's a structure, but anytime a structure implements this deref trait here and this drop trait here, it's automatically considered to be a smart pointer. And also the deref trait in Rust doesn't accept any parameters, so we have to create separate setter and getter functions and store a length to make sure that we're not setting and getting out of bounds. One of the first issues we ran into was that an OpenSHMEM, we realized we had to track the memory allocation, so we did that here with a hash map. So going back to here, as I said earlier, every time a variable goes out of scope, it's automatically dropped, but the shmem finalize function expects that all the memories are automatically cleaned up before it's called. And we didn't want the user to have to worry about cleaning up their memory before this is called. So that's why we track all memory allocations in this hash map. And when we call shmem finalize, it will automatically clear all memory before continuing on to the C portion of that function. So we wrap this in a mutex since it's a global static, and then we wrap this in the storage variable to make sure that thread safety is upheld. Another interesting point about Rust is that Rust doesn't support overloading of functions because it causes issues with Rust's strong type checking and its type inference. So one workaround with that is using Rust traits that will implement a function on different types. So here is an example of doing that, but it's important to note that when you're doing this, it expects that every time you implement this, it's the same number of parameters. So you can't really have like one setter with 2 parameters and one with 1 parameter. That just doesn't work. But we use the same like procedure for creating traits on the function. So in OpenSHMEM, there's type-specific functions like input, floatput. We're able to create more generic functions using traits, where it infers the type based on what we're calling the function on, and we'll call the correct implementation of that function. And you can see here, this is an example program of where we use that, and it infers the type of source and the destination pointer, and which is an I32, it just automatically infers that type, and it's able to call input automatically. Another important note about Rust is that there is undefined behavior when we do stack unwinding across the FFI boundary. That's because Rust and C have different ABIs, different data layouts. So it was important that we were able to catch any unwinding and abort automatically. So like stack unwinding would be when we're cleaning up memory before aborting. And so future work related to the Rust and OpenSHMEM interface would be looking into reflection, also benchmarking to assess the overhead from using Rust's FFI. And also what would be useful for everyone here is a direct Rust UCP interface. And just ending here on a cute little note, Crustacean learns Rust and he sees an error, he's frustrated. And we'd like to thank our partners at the DoD, Los Alamos National Lab, and Stony Brook. Okay, any questions?
Rebecca, Tony, thank you very much for presenting this. Any questions for Tony and Rebecca? If not, I will be asking questions. Tony, Rebecca, in terms of like OpenSHMEM, what are the plans there to bring it to OpenSHMEM community and try to standardize interface around Rust?
So you can say it again, it broke up slightly.
In terms of OpenSHMEM community, what is the plan with Rust and OpenSHMEM is to try to standardize OpenSHMEM Rust interface?
Well, we wanted to look at different approaches. So Rebecca's been working on developing the potential APIs for the Rust interface, such as these traits, so that they become methods on the symmetric variables, for example. But we really just wanted to find out what's possible in Rust and to look at different ways of doing it. And then since this is a computer science project, Rebecca's going to have to write up a report on this and do a presentation locally. So we'll include that report in the monthly reports to Los Alamos, and then people there can take that and see what they like.
Okay, cool. Thank you. Any more questions?
And just to add to that, I don't know if there probably is some interest in a direct UCX Rust interface as well. So that's something else that we could look at.